Okay, so today we will see chapter 15. This is about context-free grammar and how you convert your context-free grammar into PDA. In the previous chapter, you saw how we convert FA into PDA or PDA into FA or PDA into TG or TG into PDA. Today we will see that how we convert context-free grammar into PDA. Okay. So we have a context-free grammar, and this grammar represents the language L. So then there must be one PDA that must exist and that will accept exactly the same language. And this is vice versa. If you have a PDA and that accepts the language L, there must be a CFG. So what does it mean that if you have a PDA, you can convert that PDA into context-free grammar, or if you have a context-free grammar, you can convert that into PDA. This is what does it mean. So let's see. So this is again very systematic way of creating this. Let me actually add a blank slide into this. Does it help? No. So then it will be very easy for me to explain you that new slide here. Let me, if I need any slide here. No. Okay, this is enough. Okay, let me delete this format background. Okay, so now if you see this, that we have this uh, context-free grammar here. It's a very systematic way. So if you want to do that, so then you need to see that there's a fixed circuit from where you start. First of all, we need to see that our grammar should be in Chomsky normal form. If you have a context-free grammar, it should be in Chomsky normal form. What does it mean? It should have exactly all production rules. Either in this form, one non-terminal can be replaced by exactly two non-terminals, or one non-terminal can be replaced by exactly one terminal. So it should be in this form, and then we can start working for this. So if you want to convert your Chomsky normal form CFG into PDA, so always you need to start from this design, from this circuit, because you know that you must have one production rule which is a start production rule, and you are forced and you to always start from that start production rule, and that is a case with our design. So we are saying that whenever you want to do, you have a start, and that is start production rule, and then you need to do this push S. This is a fixed design, you always do that push S, and it should go here to one pop. This is a fixed design. You always start with this. Okay, so look at this one. So you always start with this, and now you need to see that how many production rules you have, which are like one non-terminal can be replaced by two non-terminal, like this. You have three production rules. You need to follow this design here to manage that thing. Okay, so now we will see. Okay, if you have let's take first production rule, S can be replaced by SB. So now we are saying we have this thing here, and it is S, and this is, so you know that this is push, and then again this is push, and you know that if you want to say that S can be replaced by SB, so first you want to give S and then you want to give B. So if this is a stack, so you will first push S and then you push B. And how you will do that? So you first push S and then you push B, because this will go first and this will follow that. So because of the stacked data structure, we first push S and then we push B. So we are saying if you have S, then push S, push B. So now we are saying that, okay, if this is, if you have this data structure, second production rule, S can be replaced by AB. So we have here again S and the same thing, push and another push, and it is AB. So A will come first, B will be after that. So you see this, and then we have this push A, C, C. So this is a fixed design, S, push, push. So what is this? C, C. So it does not matter here. Anything come first. So now you see this is a fixed design here. And all these three output should go and go back to your pop structure. Here. And you can connect this with itself. So this is same thing. Okay. So now we done, so all these kind of production rules will be handled by, so if you have more than this, so then you need to do more these kind of structure here. Okay, if you have more than more these kind of production rules, then once you deal with this, so then you have two production rules left, which is these one, and you know that this is one non-terminal can be replaced by terminal. So now here you need to perform read operation. Okay, so you are saying if you have, if so what is this, if you have B replaced by capital B replaced by small b, so you are saying if you have capital B, it should be read and it should be replaced by small b, and this come here also. Okay, and then you go for the second read. This is what, if you have C, C can be replaced by A. So, C, it also can be replaced by A, and you connect with this thing. So once you connect this with this, then we done this part. So if you have more these kind of production rules, you can have more read there. So once you've done that, then you want to check that whether your stack is empty or and your input tape is empty, then it should go to accept. So we will say pop if your stack is delta and your read is delta, then you should go to accept. So this is the fixed design. Always, whenever you have a context-free grammar, it should be, if it is not in the Chomsky normal form, first you need to convert that into Chomsky normal form. When we say Chomsky normal form, we mean that it should be in this format that all production rules are either one non-terminal can be replaced by exactly two non-terminal, or one non-terminal can be replaced by exactly one terminal. So it should be in Chomsky normal form, and then this is a fixed design. You follow that and you can create your, convert your grammar into PDA. So that's easy. Then what I just explained to you is written here. If you follow the stack will always contain non-terminal exclusively. Two things are possible when we pop the top of the stack, either replace the removed non-terminal with two other non-terminals, or else go to the read state. So it all can be done by the leftmost derivation in this grammar. So I mean, it says that you can follow the leftmost derivation, uh, and by using that you can convert this into, you can create any other word. We already see that what is leftmost derivation in the previous chapter. This is the same thing it is repeating. So now we are saying here we have more grammar here. Another example, if you see, this is a fixed design. Look at this one. Start, push S, pop is fixed. We have 1, 2, 3, these production rules, which are, so our grammar is in Chomsky normal form. So we have these three, S, A, B, and then look at this one, push A, push B. So we have this thing. And then all these goes back to the start. And then we have these three production rules in this form, non-terminal. So we have three reads here, and A, B, B, and it can be A, and go back here. And then you check your pop delta. if your stack is empty, read delta, your input tape is empty, accept. So now you have any word B A B, so you can trace that in this machine, and you can check that whether it will be accepted or it will be rejected. So you can check this thing, that whether if you want to trace this word here. So now look at this one. So you are tracing this. You are saying that I have this I have this word, and I want to trace this in this machine, that whether this word will be accepted or rejected by this machine. So what you are doing, we start from here and we said push S. So look at the next page. So we start, initial state, stack is empty, tape has this word. Okay. So we said, so leftmost derivation, we push S into the state, and the stack has S there, and there is no change in the input tape. So once we push S in the stack, we are here and we perform the pop operation. So when you pop, what you will get? You will get S. Okay. So when you pop from the stack will remain empty and S will come out. And now you see this machine is non-deterministic. You have B here, you have B here, you have B here. So this is hard. It will require human wisdom, that at what stage you need to move your circuit from this side to the other side. So, but we use a leftmost derivation, so that makes life a bit easy. So so after this, when you perform pop operation, it will say go to S, because you pop S from the stack, and S says push B and push A into the stack. So you push B and push A into the stack. So stack has this situation now. Still, we did anything with the input tape. And then, because we do not encounter that instruction here, once we push this, we come here and we did perform pop operation. So what you pop now, you will have B there on top. So you will pop B. Okay. So you push B and push A. So you when you perform pop, so A will come out. How he will come out? Push A and push B. Oh, so okay. So here you first push B and then push A. So A is on top. So A will come out. You are right. And then A will come out when you perform, because if you see here, you have a stack, and you have first, if you start from here, circuit goes here, push B and then push A. So A is on the top. And now when you come here and you perform pop, so A will come out from the machine and B will left. So now when you pop, it says A will come out, and now we want to see that what happened. If A will come out, then what you need to do, you have two options. Either you go here or you go here. So now here it requires your wisdom that what to do. So we are saying that we will go to this side still. So we perform again push B, push B. So now it is non-deterministic, because you want to generate this word, and so that's why you are doing this, and you follow all these steps here. So push B and then push B here again. At some stage, you will switch from this design to another design, and you switch, instead of push, you switch to the read state. And then finally, whatever you read, you will cut that from the input tape. And once you end at the accept state and the stack is empty, input tape is empty, both are delta, so then your word will be accepted. That's the idea behind that. So, I mean, I just want to show you that when it is non-deterministic, even it is a small machine, but it requires some wisdom, some human input, that how we do that. So it's not easy that you can do this by yourself. So it requires your uh, human choices, human decision, that how we do this. Okay, because of its non-deterministic nature. So you did this dry run, and you will get some answer here, whether it will be accepted or rejected. But the one thing you need to remember, that once the word will be accepted, your stack, your input tape, both should be empty. There should be nothing left in the stack or the input tape. So now it says that what I just explained to you in more formal definition, that whenever you have whenever you want to convert your grammar into PDA, so you are dealing with these two kind of production rules. So this is a fixed design for the start. This is a fixed design for non-terminal can be replaced by non-terminal for these kind of production rule. This is fixed design for non-terminal can be replaced by terminal for this kind of production rule. And then you need to check that your both input tape and the stack is empty. And then you have, so now here it's, this is one additional thing. It says if we know that Chomsky normal form does not have a lambda production, but sometime we do have that. It is not possible to work without that, or it is a scenario that you have to manage or you have to keep that lambda production in your grammar regardless. It's a Chomsky normal form. So then it says that no need to worry, we can generate this design, this circuit, which will take care of the lambda production. So you start pop from here and go back to itself, and label will be S. So this will be the lambda production. So look at this one. So we have this grammar here. So now we have 1, 2, 3, 4, 5, 6. So it means that we will have 6 push stacks in our design. So look at this one. We start, push, and we have this fixed design. And then we have this 1, 2, 3, 4, 5, 6. Because of 6 production rule, we have 6 push that. And then 1, 2, 3, 4, 4 these production rules. So now look at this one. So we have one read, second read, and third read, because S can be replaced by A or S can be replaced by B. So we merge that S, it can be output A or B. And then we have this lambda production. Look at this lambda production. So this lambda production is, you can manage here. Look at this one. So from this pop, you go back and you have the label will be S, the start. So you can come to start without any input. So this is this circuit, this only one, this line will take care of your lambda productions. And then this is a fixed design again. You want to check that your stack is empty, your input tape is empty, and then it should be accepted. So this is the only difference when you have this lambda production. Otherwise, it is same. So there is no difference in this design. But only one thing you need to see, that when you perform the push operation, it says AR1. So when you say AR1, so what does it mean? That push A and then R1. So it should be like that. So push A and then push R1. So it will be like that. So look at this one. Push, oh sorry, I did push R1 and push A. Because whatever you push, it will go first down. So you need to do this way. So push R1 and push A. So A should be on top. Okay. So that's the thing you need to take care of, that when you perform the push operation, it will be reversed according to the production rule. Otherwise, everything is good, easy. Are we good? Okay. Then we have again, this is non-deterministic. We need to perform this dry run. Let's say we have this word in our tape and our stack is empty, and we start. So we just follow the instructions, how these instructions are, how this design is, and then we just do the dry run here and start from here, perform these operations and create a table, and we can see that how we can end up with this word. And we need to figure out that at what stage you decide that from this S you want to switch from this side to this side. So this is a discrepancy. This is the non-deterministic thing here. So it requires your wisdom that at what stage you want to switch the circuit. So you have the word in front of you, or you want to accept that. So then you can choose wisely that how you want to switch from this side to the other side. And then that's it. So you dry run this one. And finally, if you read at the accept state and you see that your stack is empty and your input tape is empty, then you can accept this word. Sometimes what happen, you reach at the accept state, let's say, and your stack is empty, or might be stack is not empty, or tape is empty but stack is not empty. So even you have delta here, but you have something here. So word will be rejected. It should not be accepted. Okay. So that's the thing. So always your stack and tape both should be empty, and then you should be, and you are at the accept state, then you should accept this word. And that's it. This is a small chapter. It's not big. So any question, guys, here? Otherwise, we move to the next chapter today. No questions? Okay. If there is no question, so then without any delay, we go to the next chapter. I already published this chapter online, so you can see there. So this is chapter 16, non-context free languages. So before you see context free language, and now you will see non-context free language. You have idea about something what we will do in this chapter, but not with reference of context free languages, but with reference of regular languages. But we will apply that previous concept which you already have idea in this context free non-context free languages. Okay. So what we are saying here that let G be a context free grammar. So we have a grammar, and this is a context free grammar. And we assume that we already performed all the checks and purified it, and it is in Chomsky normal form. What does it mean? It has all production rules either in this format or in this format. So once you have this kind of production rule where you have non-terminal can be replaced by terminal, you know that once you have a terminal, it cannot be replaceable. This is a final thing you have in your thing in your word. But if you have so because it cannot be replaced, that will be the final thing. So we refer that production rule as dead production rule, that once you have a terminal, it cannot be replaced. So this is a dead production rule. And if you have a production rule like this, where you have a non-terminal and it has two non-terminal, you know that these non-terminals are not the final word. You need to replace them either with again non-terminals or terminals or combination of non-terminals and terminals. So this is replaceable. So it is not end of the word, or until unless you have non-terminal in your sentence, your production of the word is not complete. So this is not end. So it means that this is live production. It can be replaced by something. So then all these kind of production rules, we call them live production rules. Okay. So now we divide that. We are saying that we have a grammar, and this grammar is in Chomsky normal form. When we say it is in Chomsky normal form, it means it has all production rules are in this two format. Either non-terminal can be replaced by two non-terminals, or non-terminal can be replaced by exactly one terminal. So these production rules are divided into dead and live production rules. So non-terminal can be replaced by two non-terminals are live production rules, and non-terminal can be replaced by terminal is dead production rule. So now we are saying if we are restricted to using the live productions at most one each. So we are saying we have a grammar, we want to derive any word, but the live productions for the derivation process of that word, we will not use more than one time one production rule. So we only use one production rule one time, that's it. Next, we will not use that production rule for that derivation of that word. That's it. That sentence. Okay. So we can generate only finitely many words. So then it is possible that you can generate finitely many words. So you cannot, so then you will not able to generate infinite words, because once you generate one word and you only use one production rule one time, and then next for the next word you are not allowed to use any used production rule, so then at some stage your all production rules, live production rules will be finished and you will not able to generate any new word. So this is what does it mean. So it says that we can generate only finitely many words. So at each step in derivation, a non-terminal is replaced by either two non-terminals or one terminal. These are the only available production rule. Thus, if there are p productions of the form this one, live production rules, so we are saying you have a grammar. In that grammar, you have so many production rules, and you have p production rules. P is any number of these kind of production rules. So then we can say that the length of that word will be p plus 1. Okay, the set of words that contain at most p plus 1 letter is finite. So let's see the example of this one. So we have so we have this grammar here, and we can see that how we generate a word. So we want to generate this word. Okay, first of all, is our grammar is in Chomsky normal form? I can explain this here. Now this thing what I just write here is I can explain this by example. So now we have this grammar here, and it is in Chomsky normal form. If you see, all production rules are either one non-terminal can be replaced by two non-terminals, or non-terminal can be replaced by just one terminal. Okay, we want to generate this word AB. So how we generate that? We pick this production rule, S can be replaced by AB. Okay, and then we replace this A with another production rule, this one. Let me mark this one. A can be replaced by A. So this production rule. And then we have something like this. And then we use this production rule. B can be replaced by B. And we have AB. This is our desired word, what we have. Okay. So now we want to see that when we derive this word, how many production rules we used? We use three production rules, which are underlined, 1, 2, and 3. Out of these three, how many live production rules and how many dead production rules? This is live production rule because it is non-terminal can be replaced by two non-terminal, and these two are dead production rules. B can be replaced by B, A can be replaced by A. So these are two dead production rules. And I wrote it here, one live, two dead. So we use one live and two dead. So now we are saying that we can guess what will be the length of this word. So let's say machine does not see what is the length of this word, but we can guess that. What is that? How many? So our live production rules are 1. So it means in this case, P is equal to 1. So what is the length of the word? P plus 1 is 1 plus 1 is equal to 2. So look at this one, AB. Our length of the word is AB. It's a two letter word. So rule is how many live productions you will use. Count that. That will be your P, and P plus 1 will be your length of the word. That's the idea behind that. So you can predict that what is the length of my word. It's good. So now let's see this again here with reference of another example. So now we have this example here. This is that we want to generate this word BAAB. So we first use this production rule, and then we use A can be replaced by XY, this production rule, and then we use X can be replaced by B, this production rule, and then we use Y can be replaced by SX, this production rule, and then we use S can be replaced by A, and then X can be replaced by A, and then B can be replaced by B. So we use these much production rules and we get a word BAAB. So now our question is how many live production rules we use in this derivation. So if you see that we have 1, 2, 3 live production rules, it means P is equal to 3. So what is the rule? How you will find the length of the word? P plus 1. So length of the word will be 4. Look at this one. It's a 4-letter word. BAAB. So you use 3 live productions and you use 4 dead productions. And the length of the word will be P plus 1. This is your P. So it is P plus 1. So it is 4 here. Okay. So that's the idea behind that. Now look at this one. So same way you have this another example that S can be replaced by, so you want to generate this word, BAAB here. So, I mean, you can, it's the same word, but by another way of derivation. So you use that and you have 3 live productions also here, and it is again P plus 1. So leftmost derivation using context-free grammar in Chomsky normal form. So you can use leftmost derivation also, that whenever you encounter the word, always replace the from the leftmost non-terminal and then you can generate. So it can also be possible. It is the same thing, but this is more deterministic approach. Machine can easily handle that. Now we can see here either the second z is, so now what, okay, let me see here. So when we z is equal to xy, so we have this thing where the above rule is used twice, and s1 and s3 are strings of terminals and s2 and s4 are, okay, it's the same thing. So now we are saying that, let's see this example here. We can generate, we have this grammar and we want to generate something, some word, and during that process, we use this production rule one time. S can be replaced by AZ, and then Z can be replaced by BB, and then B can be replaced by Z, ZA, this one. The B can be replaced by ZA. So now if you see here that in this chain, this Z and this Z are called descendant of each other, because if you follow the bottom up parsing and you start from this Z, you can reach here. Okay, so this is called descendant of each other. This is a new concept. How we find the descendant of each other? So it means that you have two nodes which are same and you can reach there. So this is called descendant of each other. So this B and this B are not descendant of each other, because you can go up, you cannot come down. So you cannot reach to this B. This is not coming in your path. So exactly you have this A and this A. These are not descendant of each other. You can come up, 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 but you cannot reach here because it is down here. So you only go one step up. You cannot go at the same level. So these two are not descendant of each other. So it means that only Z is a node which is descendant of each other. So we just figure out what is concept of the descendant node. Okay, so if there's a node which you can reach in that tree, you can access that. This is called descendant. Either you can access directly, might be this Z will be here, so you can access directly, or you can reach there indirectly like this way. So this is same thing. It is descendant of each other. So now let's see case 2. Here it says that you have these two nodes B, B. These are not descendant of each other because you cannot reach them. So you can go up or you can go here, but you cannot reach to this node. So this is not descendant of each other. Okay. So this is a new concept which you just figure out about the descendant node. Okay, so derivation tree of each word has the property that every node has one or two descendant. It is called a binary tree. So the derivation tree of each word has the property that every node has one or two descendant. It is called the binary tree because binary tree it has two uh, childs. So because of its nature of the grammar. So now, what these are, this is some information which we just learned and what we want to predict from there, why we are doing this. So we are saying that given a context-free grammar in Chomsky normal form, a derivation tree that has the most p plus 1 rows of non-terminal has at most 2 raised to power p leaves. So look at this one, what we are saying. So we are saying that we have this grammar here and we have a derivation tree and it has p plus 1 rows. So when we say P plus 1, P means live productions and 1 rows of non-terminal has at most 2 raised to power P leaves. So we can predict that what should be the maximum size of the word we can generate by this grammar. I mean, you can generate a smallest word, but what maximum size of the word you can generate by this grammar if you have this restriction, if you want to generate that. So now we are saying that if you have this p is equal to, if this is, if you are here, so your p is equal to 0, p is equal to 1, so then maximum you can generate, the word you can generate is, so now look at this one. So this is your p, and s can be replaced by anything, and another non-terminal, and finally this can be replaced by any terminals. Okay, so if p is equal to 1, so so you can generate only one word, it says. Okay, so no, so I think this is wrong what I did. So if p is equal to 1, so then you can generate, look at this one, only you can only replace this s with any one non-terminal. So one terminal, so you can replace only one length word. So look at this, in the first row, 2 raised to power 0 nodes. So if you have, if you go to the second row, 2 raised to power 1 node. So if you have two rows here, so like at this one, it is 2 raised to power 0, 2 raised to power 1. So then it means you can generate, either replace this with one terminal, this with one terminal. The maximum size of the word will be 2. And exactly the same way, if you have if you are at the third row, so 2 raised to power 2. So 4, the maximum length of the word you can generate will be 4-letter word. Look at this one. And if you are at the fourth row, so 2 raised to power 3. So this is a formula. So 2 raised to power p leaves maximum you can generate with this thing. So now if p is equal to 3, it means that you have 3 live productions. So then how many rows you have? You will have p plus 1 rows, 4 rows, and that much number of that much size of the word you can generate. So look at this one. So if p is equal to 3, so it means that you are at fourth row here. Okay, so then you can generate, if you 1 2 3 4 5 6 7 8, maximum 8-letter word here. So exactly this way you can move on, and you can guess that. So let me actually do this for you, so we can do this, we can prove this. So if I want to generate this word, let's say s can be replaced by xy, one live production, then this x can be replaced by, let's say, sy, second live production, and then this s can be replaced by xy, third live production. So it means that, you see there, here this is our p is equal to 3, so we use 3 live production. So this is first row, second row, third row. So p is equal to 3, and then the number of rows will be p plus 1. So p plus 1 rows, because once you have the non-terminal, which is your live production, so then you need to replace that. Okay, so you need to replace this with something. So some terminal, because non-terminal is not the word. You need to replace your non-terminals with the terminals with its respective terminals. It will not increase the size of the length, but it will just replace non-terminals to the terminals, and that will be the size of the word. So this is basically, we are predicting that what will be the maximum size of the word you can generate if you have, if you have a binary, if you convert your grammar into a binary tree, and how many rows you have, and what does it mean, what is the impact on the number of rows with the live productions on the size of the word. This is what we are saying. Okay, and now we are saying that if that is the case, but let G be a context-free grammar in Chomsky normal form, and that has P production. So we make our case this thing, that if we have P productions, P plus 1 rows, the maximum size of the word will be 2 raised to power P. This we already proved this here. Okay, now we have this fact there. So now we are saying, if you have P productions, and your, so maximum size of the word will be 2 raised to power P. But let's say your length of the word is greater than 2 raised to power p. Then what does it mean? It means that somewhere in this tree, somewhere you repeat your one production. And that's the reason that because you reuse your one production rule. That's why your size of the word is bigger than whatever the live productions you have. So this means that there is a loop there in our grammar, and there is a in our design, in our PDA, and we reuse some production rule again and again and again, and that will beef up the size of the word. This is what we want to prove here. So now look at this one. Let G be a context-free grammar in Chomsky normal form that has P productions of the form live productions, and we have a word, we generate a word W. The length of the word is greater than 2 raised to power P. It should not be greater than that if we use every live production rule one time. Then in every derivation tree, for this word, there exists some non-terminal z that appears twice on the same branch. So there must be some descendant tree there. You must have in that branch somewhere z and z. So you repeat some production rule more than one time, and you must have a descendant nodes there. That does it mean? Okay. So at a tree that has more than 2 raised to power p leaf has more than p plus 1 rows. A tree that has p plus 1 rows has at most this much leaves. But if your size of the word is greater than 2 raised to power p, so it means that you somewhere reuse one production rule. Yes, this is very common understanding now. So we are using distinct production rules to reach here. It is not possible you go more than 2 raised to power p. But if your word size will be greater than 2 raised to power p, it means somewhere here it is not distinct. You repeat something, that production rule again. And if you repeat that, what does it mean? You will find the descendant nodes there. Yes, if it is a descendant nodes there, it means there's a loop here. You can beef up the word. You can increase the size of the word. This is what it means. Now look at this one. So we have this grammar here, and we are saying that in this grammar, P is equal to 4. So we have one, two, three, four live productions. Okay. So when you have four live productions, so it means that the branch that end in A has six non-terminals. So if you see this, it has six non-terminals. The branch that ends in A, it says. So five applications of productions containing only non-terminal. At least one production is used more than twice. So when you have P is equal to 4, what does it mean? 2 raised to power P. So maximum size of the word will be 16. But if your size of the word will be more than that, it means that you use something extra here. Okay. Let's say you can make another word, a size of the word, which will be 18. So it means that you are not following this formula. You are reusing this live production rule somewhere in this again. So that's the reason that you will get the bigger size of the word. So now at least one production you can use more than one time. So now if you have this thing, the two nodes which are descendant of each other, and they also have the same production rule, we can say that this is a self-embedded tree. A non-terminal is said to be self-embedded if it ever occur as a tree descendant to itself. So now look at this one. You have this X here, and it is using this production rule by, and you have this X here, it is using the same production rule by, and this X, you can go from here, here, and you can reach there. So it means this X is descendant of this X. Okay. So now and the same production rule by, it means this is self-embedded tree here. This is a self-embedded tree here. Okay. So the non-terminal is said to be, this is self-embedded non-terminal. This is so because you have you can reach there. So to be self-embedded, it must be descendant, means you can reach there and have the same production rule. So then we can say that it is self-embedded. Okay. So this is the idea behind that. So now if I can say that, am I able to find any other self-embedded tree here? Look at this one, X, BY, X, BY. So this tree and this tree, you can reach there, because if you go from here, here, you can reach there. So this is also self-embedded. Let's find some more self-embedded trees here. Uh, what about YXY? YXY. We do not have YXY. We do have Y here. Oh, yes, we have. So look at this one, YXY and YXY. These are self-embedded trees. Okay, because you can reach to this Y by this Y. So this is so it should be descendant, and then you can reach there. Let me give you one example that it is the same production rule but not descendant. SXY. No, this is good. YXYB. This is also descendant, self-embedded. Do we have any BSX? Oh, sorry. No, we don't have that. Okay. Yeah, so that's it. So do you understand that? That if you, in your grammar, you can predict that what should be the maximum size of the word. So if you have this grammar, it has 4 live productions. So maximum size of the word will be 2 raised to power p. If your word size will be more than that, it means you are not following that restriction that use one live production one time. So you are reusing that. So that's the reason that you will find the descendant tree. You will find, if it is descendant, there is a high chance you will find the self-embedded when then 2 raised to power p. So now, how many live productions here? 1, 2, 3, 4, 5, 6, 6 live productions. So it means 2 raised to power p is equal to 2 raised to power 6 is equal to 64. So maximum size of the word you can generate 64. And if your size of the word will be greater than 64, it means you will find, if it is 64, then you will not find any descendant or self-embedded tree there. If your size of the word, it is possible for you, let's say, to generate size of the word greater than 64, you will must find a descendant tree or and self-embedded node there. Okay, this is not possible. And look at this one. So you can have self-embedded trees here. So XSA and XSA. Okay, same thing here, and then here also. So you will find this one, XSA and XSA. So you have self-embedded trees here also. Okay, so this is very simple concept. Any question here, guys? So then I can start this new concept for which we did all this discussion. We will use this discussion actually to perform pumping lemma on context-free languages, and we will use these concepts there of this live production and red production, and then we can see that how we can use this actually. Any question, guys? So Gunnar, are we good?
I had a quick question about descendants.
Yes, please.
Can you put that tree back up on the screen?
Okay, this which tree?
Yeah, that's good. Any
Okay.
of it. So when you say descendant, does it only count as a descendant if it's a descendant of itself? Or could I say like Y is a descendant of S, but it's just not a descendant of itself? Does that make sense?
So descendant means that the same non-terminal you can use a second time.
So it has to be the same
It has to be the
non-terminal
same. Yeah.
to be
So
a
I mean, so X and Y are not descendant, because how they will be descendant, because this is X, this is Y, this is two different nodes. Yes. So descendant will always be same. So when we say descendant, it means the instance of same thing reuse.
okay.
Okay. So it's a instantiation of the same thing more than one time.
Okay.
Okay. So Y is not. No, it will. So V is not descendant of S, but it can be directly, it can be indirectly. Like might be you have X here, or might be you have indirect. Like in this case, you have to follow this path. And but it should be possible to reach both non-terminals by bottom up or top down parsing. So like if you follow bottom up, 1 2 3, we should be reach here. We cannot go, if you are going up, you cannot go parallel or down. Only go up, it should come on your way. If you're coming down, you should be able to reach there. So this x-axis descendant, this is descendant, this is descendant, this is descendant. So these are all descendant of each other. So if I can mark, I can actually, I'm sorry, this is not descendant because it has different production rule. It has A here. So when we say descendant, it should also be the same production rule, x by x by. So this is descendant by. This is also not descendant. These two are not descendant. So this is maximum descendant. Make sense?
Yeah.
So Jacob, any other question? James, Kevin, Quinton has some question. Let me read. When generating these trees, how do you know when to use the non-terminal substitution and when to use the non-terminal? And or you can have the word in your mind, that whatever the word you want to generate, so you have the target word in front of you, and so then you can use that. Look at this one. Okay, it's a very good question. So look at this thing. We always have a target word, what word you want to generate. So we want to generate this word, and now you will follow, let's say I follow the leftmost derivation method, and I want to generate this thing. So then I can use accordingly whatever the production rule I need to use to generate this word. And once I generate this word, then I will see how many production rules I use. So there it is. So you have the target word in front of you. So Quinton, is this answer your question? Okay. So I mean, mainly we want to use this concept here for the size, for basically to use in the pumping lemma. So now we are saying that, let's see this. The pumping lemma for context-free languages. So let G be a context-free grammar in Chomsky normal form that has P productions of the form live productions. So grammar is in a Chomsky normal form. It has a P productions of this form, and the size of the word is greater than 2 raised to power p. So it means that somewhere you are reusing some production rule again. What are those? How we can figure out? So we are saying that we will apply pumping lemma on our grammar here. So what we will do? So we have a word. Our job is to find the loop in our word. So we will divide our word. So when we talk about pumping lemma on regular languages, so we have this formula. So we divide our word into 3 parts. In this case, we divide our word into 5 parts. Okay, U, V, X, Y, and Z. So now X is not lambda. X will never be lambda. You must have X in your word. It will never be lambda. Okay. For V and Y, this thing, V and Y, one can be lambda at one time. Either V is absent, Y is not there, Y is there, or Y is not there in your word, V is there, or both are there. It will never happen that you are missing V and Y both in your word. U and V, both U and Z, both can be lambda, both can be there, either one can be present, it has no restriction. And you can beef up your word by V raised to power n and Y raised to power n. So you have a word you divide your word into 5 parts, and your word will have X must be there in your word. This will never be lambda. It must be there. This one or this one, either one can be lambda or both. It's not necessary that it must be either one can be lambda. No, you may have V and Y both there. You may have one is missing, any one is missing, but you will never have this scenario that both are missing. For U and Z, both can be missing, both can be present, either one can be present. We have no restriction for them. X must be there. But the word can be beefed up by these two words, y raised to power n, v raised to power n, and y raised to power n. Okay, so this is the restriction for our word. And now we will see that what is U, what is V, what is X, what is Y, what is Z in our grammar. So now let's say you have a tree here. Okay, so now your the at the leaf level, if you have a descendant node, let's say you have this thing, you start production rule from S, and then you are doing something here, you have a lot of other things, and you are doing that, and you generate this production rule PQR. And let's say this is a descendant, you have again PQR. Okay, so this is again Q and this is R. So now these two are descendant of each other and they are self-embedded. Now we have this thing, and this is at the leaf level. Okay, all those letters which you generate from outside of this thing, this the top tree, it will be your U. And the same is case on the left side, on the right side, that will be your Z. Any letter which you generate from this lowest self-embedded tree, this one, this X and R, this will be your X. Anything which is from the above self-embedded tree, this will be your V, and on the other side, this will be your Y. This is how you can generate a words. You can divide a word into 5 parts. So what you are saying, let me explain this again. So we are saying that we have a word and we divide this word into 5 parts, and we have a self-embedded tree here. The lowest part of self-embedded, whatever so it has Q and R here. You replace this Q with terminal, you replace this R with terminal, and this will be your X. Okay, now you are generating some words here which is not part of this from the outside tree, but only after the descendant, the top descendant. So all these letters will be V and this will be Y. And above this tree, all letters you generate here will be Z and U. So this is the way you can generate, you can divide your word into 5 parts. And all this discussion which I just explained to you is written here in good English. So now X will never be lambda. This will never be lambda. V or Y both can be there. Either one can be there, but it is not possible that both cannot be there. U and Z both can be there. Both cannot be there. Either one can be there. It has no restriction. So now we are saying that if that is the case, so let's see, and what I just explained to you is written here. So now look at this one. So you have this production rule where S can be replaced by SA, and then S can be replaced by A, and A can be replaced by A, and this one. So now our job is to figure out what is self-embedded tree here. So look at this one. So this is S, and this S is two descendants. They have same production rule. So it means we have these two self-embedded trees. One is this and one is this. And this is parent one and this is, so parent one I put this way, and this is a child one. So this is your, and now how we divide our word. This is your X. Look at this one. This is your X. We are not able to generate any word from this S here. Look at this one. We have nothing here. Nothing here is coming from this side. So we do not have any V. So V is lambda. Look at this one. And above S is from, we start from S, so there is nothing coming here. So before S, so U is lambda. We do have, look at this one. This is A is not belong of this tree, but this belong of this parent subtree, self-embedded tree. So this is your Y, and you are not getting anything from here. So this is your Z is lambda. Make sense? So this is basically this way how you divide your word and figure out that where you have a loop here. So look at this one. So now this will tell you that how you beef up your word. So you have S. So this is your P, and this is your X. Any word among from this is self-embedded. This is self-embedded. This is self-embedded. So all these are your V. All these are your Y, and above this is your U and your Z. So now you can see that this way you can. So now because, and now this will make sense that V raised to power n and Y raised to power n. You can have more than one V here. You can have more than one Y here. And look at this one here. More than one V, more than one Y. So you can beef up the word by these V and Y. You can increase the size of the word by V and Y. Make sense? So now this is some, we can use the new symbol which is called, you can derive, and also you can use them as many times, because if you see here, so you are deriving a new word and you are using this production rule, this one, as many times you want to use. So it has this symbol, this one, that you are deriving and you are performing the closure property, which is infinite. So you can write that here. So because of this, S can be, so U P Z, and so U V P Y Z. So this way you can add, you can generate your word as many times by this way, because this means that you can derive also, and you can use apply closure property on that also. So now how we write this here. So look at this one. S, you can derive this U P Z, and then V P Y, and then X. So you can beef up the word, and finally you have your word back. And here you have, this is X, this is V, and this is Y, and you do have U and Z here also, which is coming from the top side alternatively. So main thing you need to understand, any set of letters generated by the most lowest self-embedded tree will be X, and all those letters which you generate from the parent self-embedded trees will be, if it is on the left side, will be V, on the right side it will be Y. Any letter or any letters generated above than the parent self-embedded trees will be on the left side will be U, on the right side will be Z. That's the idea behind that. So this way you will divide your word into 5 parts, and V and Y are have raised to power n. It can be more. X must be there. These two can, either one can be there. U and Z both can be there. Both cannot be there, or either one can be there. We have no restriction with that. So let's see here. We have this PDA. This PDA is wrong. There is no PDF. So again, sometimes for the non-regular languages, it is hard to draw the PDA. Look at this one. This PDA can accept. So we have this language AN, BN, AN, like same number of A's, same number of B's. So like this. So this we tried to design this, but we figured out that it is hard to draw the PDA for the non-regular languages here also. So if you dry run that, so this machine will accept this word A10, B8, A12, whereas this is a violation of this language, because it is 10, it is 8, it is 12. It should not accept this one. It should accept all A's, B's, and A's with the same number. So it is hard to draw the PDA for the non-regular languages also. And that's it. So these two chapters are small, actually, it's not big. So I think that we finished here. So any question, guys, about bumping lemma, if you have any question about bumping lemma for the non-regular languages. So Nikhil, are we good?
Yeah, we're good.
Okay. So yeah, that's good. So now let me stop recording this.